minds on the 30, 45, and 60 degree angles. We'll do it pretty quickly. And when we're dealing with the 45, 45, 90 triangle, we're thinking about that. And last class, we talked about you can pick any side length you want for these legs. These legs have to be the same in a 45, 45, 90 triangle. And the number that we ended up seeing frequently was root 2 over 2. And I'm just going to pick root 2 over 2 for these two sides. And what's that going to make the hypotenuse then? So square, square, add, and we get 1. Okay? Does everybody agree? Square root of 2, root 2 over 2 squared is 2 fourths. 2 fourths plus 2 fourths is 4 fourths. 4 fourths is 1. And we said last time we can pick whatever we want for that side. You can pick 1, and that's what we did last time was pick 1. What's your last name?
My name is
That's your last name?
Yeah.
And are you on the roster?
I'm not in class.
Okay.
At your side job.
Oh, okay. Yeah, we'll talk during the break. Okay, so I'm going to pick those two numbers. Today we'll probably talk a little bit more of why it's nice to have that hypotenuse being 1. But for now, it doesn't matter. But eventually it'll be an important feature. So when we pick our sine of this angle, 45 degrees, sine is what ratio? What did we say last time for sine when we're looking at a triangle? And to get that square root of 2 over 2, what were the sides of the triangle that we used for sine? Opposite over hypotenuse. So sine, by definition, is opposite over hypotenuse. So for any right triangle, if you focus on your angle, the sine of that angle is opposite over hypotenuse, always. So if we look at that 45, sine is opposite, root 2 over 2 divided by 1, so we get root 2 over 2. And the same is going to be true for cosine. Cosine is root 2 over 2, but here we're doing adjacent over hypotenuse, root 2 over 2. Tangent, opposite over adjacent, which is 1. The other three are reciprocals. And what we saw last time was that if you take the reciprocal of 2 over root 2 and you rationalize that denominator, you are going to end up with just root 2. So these two reciprocal functions, root 2, and the reciprocal of 1, of course, is 1. All right, so those ones, got to get down pat, and it's really important to sort of understand this process of how to generate them. You know, later on, as you're taking other math classes, if you forget, you should always be able to come back to a right triangle, use the Pythagorean theorem to create some sides that work, and then remember the ratios. All right, the other one that was super important that we did last class was the 30, 60, 90 ratios. And remember that what we did was split this triangle like that. And what we did was choose 2 as the side length, which made each of these pieces 1 if we split this. So there's our 90, there's our 60, there's our 30. And we used the Pythagorean theorem to calculate the height there is root 3. Pythagorean theorem. Okay, so then our trig function values, let's do a quick review for 30. And what would sine of 30 be? So I hear a 1/2. The ratio for for sine is always opposite over hypotenuse. So we go to our 30-degree angle. The side opposite is 1. The hypotenuse is 2, so 1/2. Yes, 1/2. And then what about cosine? So cosine of 30 degrees is the adjacent leg. The adjacent is √3 over the hypotenuse. Is √3 halves, √3 over 2. And then tangent, opposite over adjacent. So we got the 1 over √3, but we rationalize that, and we get √3 over 3. And then we take the reciprocal of each of these and rationalize them. So here, when we flip it, we get 2 divided by √3, so we have to multiply top and bottom by √3, and we'll get 2 √3 over 3. Flip that one, and we get a 2. Okay, so those you want to have down pat. Down pat. And then the 60-degree one, we can do it in 2 ways. We learned a really cool technique at the end of last class that cofunctions of complements are equal and 30 and 60 are complementary. So let's approach the 60-degree one that way, just as a refresher of that important concept that cofunctions of complements are equal. So if we want to use that concept here, sine has what as its cofunction? Cosine is the cofunction for sine. So if we want the trig function value here, instead of going to the triangle, we could say the cofunction of sine is cosine. Complement of 60 is 30, so they have to have the same value. √3 over 2. Cosine, again, the cofunction is sine. Complement is 30, so 1/2. The cofunction for tangent is cotangent. That's right there. And 30 is the complement, so those two should match. And similarly, these two should match. And then these two are just reciprocals. Or you could go up there and match them with their cofunction. All right, so those are the important ones. And super important focus on the, oops, that's a square, not a rectangle, on the primaries, sine, cosine, tangent. Those are the most important ones, because the others are just reciprocals. You've all mastered the idea of reciprocating a fraction by now. So important ones, sine, cosine, tangent, of those 3 special angles, 30, 45, 90. We'll do it a ton, these ones, this semester. All right, so let's go ahead and get over here. And we're dealing with angles right there that are not special. When we say special, we generally mean a multiple of 30 or a multiple of 45. That's typically, some people reserve special angle to just mean 30, 45, or 60. But usually we'll get a little looser and just say it's a special angle if it's a multiple of 30 or 45. Because what we will see very soon is that by knowing the trig function values for 30 and 45, you know them for all multiples. We will see that shortly. Now, if you have an angle that's not a multiple of 30 or 45, or you don't have a triangle that has the correct side lengths for that angle, you've got to use a calculator. So for these two up here, we have to type it into our calculator. Now, if you look at most calculators, they will only have sine, cosine, tangent, and they won't have cosecant, secant, and cotangent because they have limited space, and we already know that cosecant, secant, and cotangent are just reciprocals. So you can hit your reciprocal button. All these calculators have a reciprocal button. The reciprocal button says x to the minus 1. That is the reciprocal button. So all of these calculators will have an x to the minus 1, and that will take the reciprocal for you. So cosecant of 45.2. That is the reciprocal of sine. So this is 1 over sine 45.2. So you can type into your calculator 1 divided by sine of 45.2, or you could type sine 45.2 equals and then hit your reciprocal button. Whatever you want. And if we go to the nearest hundredth, this would be 1.41. Nearest hundredth. For this second one, tangent, there is a tangent button. And so on your calculator, you have to know how to get to the degree, minute, second menu. On these little guys, it's just right up there, degree, minute, seconds. And all the calculators will have that somewhere. Some calculators, you have to hit the menu angle first. Some calculators, you hit the math menu, and then there's a DMS, the degree, minute, second tab under the math menu. Whatever it happens to be on your calculator. So I'm typing in tangent 63. I'm going to the degree, minute, second button and choosing degree. And then I'm typing in 48, going to the degree, minute, second menu and grabbing minutes. And we should get to the nearest hundredth. We will get 2.03. So just make sure that you're functional with your calculator and you can get some basic trig, evaluate some basic trig functions. Okay. Now, on your calculators, you should also see 3 buttons that correspond to inverse sine, inverse cosine, inverse tangent. And first, let me warn you that inverse sine of some number, I'll call it t, is not the reciprocal of the sine function. Okay? That's not the reciprocal. Inverse sine is an inverse function. In college algebra, you learned a lot about inverses and how to find inverses. And in the simplest way to think about an inverse, if you think about a function in its simplest sense is just a collection of points. It's a collection of ordered pairs. And we look at the graph to see a picture of those ordered pairs. But a function in its simplest sense is just a collection of pairs, ordered pairs. And an inverse function, you just take that collection of ordered pairs and you flip all the x's and you flip all the y's. So that's the concept of a function and an inverse in the simplest terms possible. Collection of points, flip all the x's and y's, and you get the inverse. And the primary inverse you dealt with in college algebra was the inverse of the exponential function. And the inverse of the exponential function is the everyone jump at once. What's the inverse of the exponential? Pardon? Not a root. Inverse of a square would be the root.
Logarithm?
Logarithm. Exactly. The inverse of exponentials are logs. That was the whole point of studying logarithms, is that they're the inverse of an exponential. So a lot of times you were dealing with exponential equations and the variable is up there in the exponent spot. And you can't solve, before you know how to do a logarithm, you can't solve for a variable that's up in the exponent position. So the whole point of learning logs is that logs were the inverses of exponentials, and applying a log to an exponential allowed you to bring that exponent down and you could solve for that exponent. Okay? So logs were studied so that you could solve exponential equations, because the exponent was where the variable was, and logs allowed you to bring it down. Similarly, the inverses for the trigonometric functions are going to allow us to solve for the angle. Okay, so right there, the variable is inside the trig function. We can't unravel it like you can with algebraic functions or algebraic equations where you can just sort of move stuff around. So at this point in the class, what I'm about to show you only works if theta is acute. So this is really important right here. So if you have an acute angle, you can do the following, but only if your angle is acute. We will see shortly that this is not always true if you have a non-acute angle. So for each of these three, I can solve for the angle by doing this. Again, the one constraint is that you have to be dealing with acute angles. Theta has to be acute. That has to be true. Okay, and we're not going to use a lot of inverses early in the semester, but I want to introduce you to the concept right now because it's very common when we're talking about cosecant and you're doing a reciprocal. It's very common to get tangled up and think, oh, that must be cosecant, inverse sine. Right? When you look on most calculators, inverse sine is above sine. So it sort of makes you think like it might be the reciprocal of sine, but it's not. It's an inverse function. Okay, so this would be true. That is true. Those three statements are true. Now, the one rub with this particular set of three examples is that all three of these actually should look like really familiar ratios already. For these three, you really shouldn't have to go and type it into your calculator because those ratios should look darn familiar from what we just did. The 1/2, the root 3 over 2, and the root 2 over 2. Those three ratios, anytime you see one of those three ratios, then you should be thinking special angle. 1/2, root 2 over 2. There should be a big bell that goes off in your head when you see one of those ratios, and that bell should be telling you that you're dealing with a special angle, a multiple of 30 or 45. And shortly we will see that we can extend these particular ratios if it's plus or minus one of these also. That should be sending off a bell that, oh, that's a special ratio. So I don't really need to use my calculator. I can go look at a picture and figure out what those angles are. Okay, so, oops, way too far. All right, so this is mathematically correct. You could type that into your calculator and get an answer, no problem. But what I want to think about is this geometrically also. Sine of theta equals 1/2. What that's asking for is the angle that has a sine value of 1/2. That's how you would think of that equation right there. This equation is looking for the angle that has a sine value of 1/2. And so if we go back here, we can look and say, oh, right there. This is the angle that has a sine value of 1/2. Okay? So that's going to be 30 degrees. Jumps. Softer, I guess. So that the answer here is going to be 30 degrees. And we're going to see very shortly that, and you all have seen a graph of the sine function. You've all seen this somewhere. You know, the sine function is this periodic function. It repeats itself every so, again and again and again and again and again, forever in both directions. And you can see that since this graph is going to repeat itself again and again and again and again and again, there are actually an infinite number of angles that have a sine value of 1/2. We will study that in great detail. But we have this caveat here. We want the acute angle. We want to focus on quadrant 1. Just the single angle in quadrant 1 that has a sine value of 1/2. Next one, cosine theta equals root 3 over 2. Blindly you can type it into your calculator, absolutely, because you're looking for an acute angle. But if we want to think about special angles, we'd be saying to ourselves, okay, what acute angle has a cosine value of root 3 over 2? We comb through our special angles. Oh, right there, 30 degrees is the angle that has a cosine value of root 3 over 2. It is the special angle that has a cosine value of root 3 over 2. It is the acute angle. So, what did I say, 30 degrees? Well, that will be our answer for that one. tangent of theta equals root 3. So again, we can go look at our table and say we see the root 3 for a tangent value. These three up here, 1/2 root 2 over 2, root 3 over 2, those are special ratios for sine and cosine. And then for tangent, the ratios that should give us a little trigger are 1, and then root 3 or root 3 over 3. Those are the ones that should clue us in that we're dealing with a special angle. And so our answer here is 60 degrees. That is the acute angle with a tangent value of root 3. Any questions? I provided the answers in degrees. If you are blindly typing into your calculator, you always need to be careful of the mode. Your mode could be in radians or it could be in degrees. And we'll study radian angles very shortly in the next couple of weeks. For now, we want to make sure that your mode is in degrees or you're not going to get the same answer that I have here. When you get to calculus, most of your trig is going to be done with radians instead of degrees. We'll talk about why, and there's a great reason why. Okay, so unless there's a question, we'll move on. And we'll do one more of these guys. Is that the same one we did last time? Did we do an 82 yesterday? Was it a different one? I can't remember off the top of my head. I picked a couple out, and I should have been more careful, I guess. Okay, so here we're given, this is going to be an example of this important relationship, that cofunctions of complements are equal. The list of cofunctions is right here. We only have 6 functions we're dealing with for this entire semester. 6 functions. Whew, it's not a lot. 6 functions. Unlike college algebra, where you looked at like 6 million types of functions, rational functions and log functions and exponential functions and polynomial functions, polynomials of higher order, square root functions. We, this entire semester, will be dealing with just 6 functions. Not too bad. We also will be looking at their inverses. So you could say, oh, well, the inverses are different. But they're, when you think about a function, its inverse sort of comes along for the ride. Okay. Down here, our question says, figure out what sine of 82 is given information above. So cofunction of sine is cosine. Complement of 82 is 8. So in order to figure out that, we need to know that's going to be equal to cosine of 8. So those have to match. 0.9903. Cosine of 82 will be equal to sine of 8. Go up there, we look for sine of 8. That's 0.1392. That. Tangent of 82 should be equal to cotangent of 8. So we go up, figure out cotangent of 8, 7.1154. And then cosecant of 82. Of course, you could just type that into your calculator and click on your reciprocal button. That would give it to you. If we use our cofunction of complement technique, the cofunction of cosecant is secant. Secant and cosecant are cofunctions. So we should be able to go to secant of the complement, so secant of 8. Secant of 8. Yeah, they have these out of order for some reason. 1.0098. And secant of 82, cofunction is cosecant. So we go to cosecant of 8, 7.1853. And then tangent of 8, 0.4 1405. All right. So important concept, cofunctions and complements are equal. One observation, sine and cosine, both less than 1. And we talked about that a little bit last time. Because sine, if you think of it as a ratio, is opposite over hypotenuse, and the hypotenuse is the longest side of a triangle. If you're dealing with an acute angle, the value of sine is always between 0 and 1. Can never be equal to 1, can never be equal to 0, can never be more than 1, can never be less than 0, if you're dealing with an acute angle. Same for cosine. That automatically forces cosecant and secant to be greater than 1. If you take a fraction, a number between 0 and 1, and you flip it over, you get a number bigger than 1. Right? Flip 1/2, you get 2. Flip 1/3, you get 3. Flip 1/10, you get 10. Flip 1/100th, you get 100. So you flip a fraction, a true fraction, a proper fraction, something that's between 0 and 1, you're going to get a number greater than 1. So that's just an important check. As you're putting down your trig function values, sine and cosine can, they're restricted. They have to be small. All right, so let's jump to 6.2. And in 6.2, we're going to solve right triangles. Later in the semester, we'll solve other types of triangles, triangles that aren't right, called oblique. We'll do that later. So solving a right triangle, there's 6 pieces of information in a right triangle. 3 sides, 3 angles. In order to solve the triangle, we need 3 pieces given to us. So with this particular triangle, the 3 pieces they've given us, the hypotenuse, they've given us the right angle, of course, if it's a right triangle, and they've given us that. So those are the 3 pieces that we've been given. We need to find the other 3 pieces. And angle A is probably the easiest to get at. That must be 45 degrees. Any question on that? We know the sum of the 3 angles is 180, and since 90 is down in the corner, that leaves 90 to be split up for the other acute angles. 45 and 45 are the 2 that add to 90. So that has to be 45. And now we have a couple of things that we can do here. We're dealing with a 45, 45, 90 triangle. That tells us that the 2 legs have to be equal. So A and B have to be the same there. Everyone agree? A and B have to be the same. So we could use a Pythagorean theorem approach. We could say that, oh, B is equal to A. Those are the same. So we could say A squared plus A squared is equal to 100. So 2A squared is equal to 100. So that tells us that A squared is equal to 50. And that tells us that A is the square root of 50. A is a distance. It's the length of a side of a triangle, so I don't need the negative square root of 50. And that is 5 times the square root of 2. 25, right? Square root of 50 is the same as square root of 25 times 2. And square root of 25 is 5. So that is the length of A, which is also the length of B. Because those are equal. So that is a pretty standard way to go at it. Pythagorean theorem is something you're super familiar with, so that always works with the right triangle. It only works with the right triangle. Now here's another technique using a similar angle technique. We looked at this triangle last class. We talked about it a little bit right when we started. That's a 45, 45, 90 triangle where I've chosen 1 as the leg length, and that forces root 2 to be the hypotenuse length. These triangles are similar. Similar triangles have common ratios. Similar triangles have common ratios. Triangles are similar if their angles all match. Okay. So those are similar. So you could say to yourself, another way to do this would be, oh, if I multiply this, I can multiply all three sides by the same number and get that triangle up there. If I multiply by the correct number, I can figure out what this side length has to be. Now, we already calculated it, so it's pretty obvious now that, oh, it's got to be this number. So if we multiply that number by each side, we will get a similar triangle that has a hypotenuse of 10 that matches this. And double check in your mind. Root 2 times root 2 is 2. 2 times 5 is 10. So that would also be a way to get at it using similar triangles. Okay, let's take a peek at that one. We'll go through this one, and then I'll give you one that you guys can work on. I'll do one of these that has the degrees in minutes. The obvious place to start is H. You've got two angles of the three. Go ahead and get the other one because that's done by subtraction, so that's probably the easiest to do. So H will be 90 degrees minus 28 degrees 34 minutes. And here's the simplest way, I think, to do subtraction is to stack them. And I'm going to borrow 1 degree from the degree column and turn it into minutes. 60 minutes is 1 degree. So 89 degrees, 60 minutes is just another way to write 90 degrees. 89 degrees and 60 minutes is really 90 degrees. 89 degrees plus 1 degree. So it's 90 minutes. It's 90 degrees. 90 degrees. And now we can subtract the minutes from the minutes, the degrees from the degrees, and we'll get what we're looking for. So 60 minutes minus 34 minutes gives us 26 minutes. And then we subtract the degrees. And we're going to subtract 9 minus 8 is 1. 8 minus 2 is 6. So that is going to be the measure of angle H. Like that. There's H. And one other thing I want to point out is that we're about to find some side lengths here, and we're going to be using non-special angles. We're going to have to type it into the calculator. We're going to get these huge decimals. What we want to do is be consistent. We're not going to do it the same way they would do it in chemistry or in hard sciences. In math, when we're dealing with a triangle, if one of the sides that's given, or the only side, is rounded to the nearest tenth, we will round all the sides to the nearest tenth. If you get into some technical sciences, they will say if the angle inside the triangle is measured to the nearest minute, then the side length should be measured to the nearest 100th or something. There's some scientific way that you can match precision of angle to precision of side. For us, keeping it simple, if one side is to the nearest tenth, we'll round all the sides to the nearest tenth. Okay? If one angle is to the nearest minute, we'll round all the angles to the nearest minute. If one angle is to the nearest tenth, we'll round all angles to the nearest tenth. If one angle is to the nearest degree, we'll measure all to the nearest degree. So we'll just be consistent with the three that come along with the triangle. The three sides are the three angles. So that's to the nearest tenth, so we're going to measure those two to the nearest tenth. All right. Now, we did not do any rounding when we came up with this angle, that measure for H. So we can use either of those angles. If you were in a triangle where you started with some decimal angle here and you had to round to get this angle, then you'd want to use the unrounded angle. Always try to use unrounded data, or data that appears to be unrounded. If you've rounded it, then you know it's been rounded, so try to avoid that. Let's go for H. Lots of ways we can get H up here. Give me a trig function you want to use. Tangent. All right, let's use tangent. Of what angle? So let's go. So our choice, tangent of 28 degrees and 34 minutes. We could have used the other angle. We could use another trig function because we have two different angles that we can use here. Now there's one trig function that, there's a couple of cases that won't work. We don't know h or f, so we definitely don't want to pick a trig function of this angle that uses both of those, because then we'd have two unknowns. Okay, so we wouldn't want to use what function if we were focusing on 28 degrees, 34 minutes. We wouldn't want to use which trig function? Cosine, because cosine is adjacent over hypotenuse. And when we're at angle G, adjacent is h, unknown. Hypotenuse is f, unknown. So we wouldn't want to use cosine of that, but we could certainly use sine. And if we were focused down here, we wouldn't want to use sine, because sine of angle h would be unknown over unknown. But we can use all the others. Usually, we would stick to sine, cosine, or tangent. You wouldn't want to use the reciprocal functions, but you could. Okay, so tangent of 2834 is going to be opposite over adjacent. That's the definition of tangent. So opposite over adjacent. We're trying to find h, side h. So we have to do a little manipulation, I guess I should say. So we need to isolate the h, so we're going to pull the h to the left by multiplying. Move the tangent to the right by dividing. So the next statement here would be h, multiply both sides by h, and then I have to divide by tangent. And then here's where we type it into our calculator. So type that in, and the way I am going to type this in, I'm going to type in that trig function first. I'm going to type in tangent 28, go to the degree menu, grab degree, type in 34, go to the degree minute second, grab minutes. All right, so I've typed that tangent in. Now I'm going to hit the reciprocal key because it's in the denominator, equals, and then I'm going to multiply by 17.3. Put the trig function in first. That's what I am doing. And let's see, I think we agreed that we're going to the nearest tenth. So to the nearest tenth, 0.77 rounds to 0.8. So that would be our side length or side h. So here is a good example of a rounded answer that we now want to just preserve and not use for a future computation, because we definitely rounded that answer. Okay. One way to find f is with the Pythagorean theorem, but we would opt not to do that because that would include using h, which you just rounded. Now, if you wanted to save this long answer on your calculator, you could do that. Every calculator has a really easy store feature now. So you could do that if you didn't use the rounded answer. And on these little calculators, there's an STO button on the bottom left. And if you hit that, if I hit STO, there's a group of letters across the top, and I can choose whatever letter I want to save it in. If I just choose A and push equal or enter, that's now stored in the letter A. And if you look at the blue letters above store, there's an RCL, which is recall. And so you can then recall any letter that you've stored a value in. So you could use the Pythagorean theorem if you use that more complete answer. But that said, this still is rounded. Even if you go all the way out to whatever number of decimal places it is, it's still rounded. I mean, it's so precise that far out that we could use it, no problem. But keep in mind that it still is rounded. These trig function values are irrational. You learned in college algebra the difference between a rational number and an irrational number. Irrationals go on forever. They're decimals, no repeating, no pattern. Rational, as a decimal, either terminates or it repeats with a pattern. This is a good, lots of irrational numbers in this class. All right, so the last thing that we're looking for f. And if we look up here and let's just keep focusing on the 2834 since it's in the triangle, we can see it. What trig function would we want to use for that? We use the 2834 and the 17.3. Yeah, we'll use the sine function. Very good. So we'll say the sine of 2834 is equal to 17.3 divided by f. And then we have a very similar type of math that we have to do, very similar to what we did over here. We'll multiply both sides by f and divide both sides by the sine value over here, sine of 2834. And then we'll get f. We'll round it to the nearest tenth. Has anyone typed that in yet? So however you want to do it. You certainly can type it all in directly, 17.3 divided by sine. Lots of different ways. Whatever you prefer. All right, and I'm getting 36.2 to the nearest tenth. Do we have any confirmation? Somebody else get that number, 36.2? All right, we'll go with it then. Chances of us both making a mistake are so unlikely. Okay, any questions on solving a triangle? You ready to do one yourself? Let me put in a slide. All right, so you guys do this one. Let's suppose that this angle is 35 degrees. That's that. And let's suppose that this side right here, I'm going to call it 13.1. And let's call this, I'm going to start using Greek letters for angles and triangles. We'll do that a lot later. Let's just call that angle alpha. The side opposite alpha we would call side A, so that's given. Side A is given. Alpha we don't know. We're going to call this side B. We'll call this side C. Call the hypotenuse side C. All right, so solve that triangle. And I'll put another one up here where we use DMS. Need any help? Jessica and I will walk around and point you in the right direction. Hopefully. Yeah, so this one is the ratio. Then choose to solve for B first. You would want the trig ratio that uses this angle, this angle side. So first thing, two legs. There's only one function. Yeah, yeah, that's right. Makes sense. Oh, that's your phone. I was like, whoa, look at that screen. That's like the best looking calculator screen I've seen. Like, oh yeah, it's a phone. The calculator screens are still terrible mostly. All right, let's go ahead and solve this first one. Let's see if I can find my marker. So when we look at this first triangle, we can solve for alpha first. I think that makes a lot of sense, is to go for the angle. If we have two angles, solving for the third angle. So of course that's going to be 90 minus 35, which will be 55 degrees. So we'll go with the easiest piece first, solve for the angle. All right, now we have to do the trig. Now we have to figure out B or C. And the thing to keep in mind, we'll use the angle 35, and we want to use the side 13.1. So we have to identify to ourselves what the trig function is that's going to use, if we're solving for B. We need the trig function that uses these three pieces of data. So from the angle 35, from that perspective, we want to use the opposite over adjacent. Right, that's the ratio that's going to incorporate the B and the 13.1. It will be opposite over adjacent. So what trig function uses opposite over adjacent? Tangent. So that will be the trig function that we choose to use. So we'll say tangent of 35 degrees. That will be equal to B divided by 13.1. And then we have to do that similar algebra, arithmetic that we did with the previous problem. We'll multiply both sides by 13. Oh, actually, this one's even easier. We just multiply by 13.1. I'll put the unknown on the left, though. So 13.1 multiplied by tangent 35. And what should we be rounding this to? Yeah, we're going to go to the nearest tenth because this side is the nearest tenth. So somebody tell me what you got for that, for the nearest tenth, to the nearest tenth. 9.2. Okay. 9.2. Thank you. And then we go back up. We have to find C. And we sort of keep in mind that we just rounded B, so let's sort of think of B as off limits. And let's think about these three. So we ask ourselves, what's the trig function that's going to take into account these three pieces of data? From the 35-degree angle, we're thinking adjacent over hypotenuse. So that is cosine. So cosine of 35 is going to be 13.1 divided by, we call it C, I believe. So now we have to solve for C. So we multiply both sides by C, divide both sides by cosine of 35 degrees. Type that into our calculator, round it to the nearest tenth, and what do we get? 16.0. Sound good? Some confirmation. I don't see anyone disagreeing, so I'm assuming that means yes. All right. Now I'll jump over to this one. Here we're going to solve for alpha first. Again, if you're given two angles in the triangle, that's generally a pretty safe place to start. Now let's see. So that's to the nearest tenth. So this other angle will be to the nearest tenth. So that's going to be, what, 60.9? Is that right?
Yes.
All right. Thank you. And now we have to do the trig. So we can solve for A or C first. It doesn't matter. Let's go for A. So if we're going to solve for A first, we need to say, what trig function uses those three pieces of information? Tangent. Once again, tangent, because we have two legs. Tangent's the only function of the primary three that uses both legs. Right triangle has three sides, and those two are called the legs. Three sides, two legs. And tangent of 29.1 degrees will be 15.02. So we're going to round all our sides to the nearest 100th. Multiply by a, divide by tangent. And we will have this to type into our calculator. We're going to round it to the nearest 100th. And what do we get when we type in all that? Say again, louder.
27.0.
So that's 27.0. All right. And if we're going to the nearest 100th, we would go 27.00. And our last goal is to solve for C. And again, we just rounded that A, so we'll keep it off limits for now. We would rather use these two pieces of information. So we're going to be, from the perspective of this angle over here, 29.1, we're opposite over hypotenuse, and that is the sine function. So sine of 29.1. Opposite, which was 15.02, divided by the hypotenuse, which is C. Multiply and divide. We'll type that expression into our calculator. And when we type that into our calculator and round to the nearest 100th, we get 30.88. Thank you. And we got it. Not too bad. Any questions on any of the procedures? Does that feel pretty good? Next slide. Distance. I will do, let's do this one and then we'll take a break after this one. It's always good to take a break after a word problem, especially when there's that many words in it. It's like, and a lot of these word problems, there's a lot of words you don't even need to look at. A lot of times you can look right at the picture, if there is a picture. Okay, so reminder, angle of depression and an angle of elevation, those are both from the horizontal. An angle of elevation is up from the horizontal. An angle of depression is down from the horizontal. And this says that we have a plane, aerial photographer, and we have 475 degrees as the altitude. That's how high the plane is flying. And a distance of 850 feet from the farmhouse. So we have a farmhouse right here, 850 feet line of sight. Altitude of the plane is 475. What's the angle of depression from the plane to the house? So our goal is to look for that angle of depression, which they're calling theta. And one of the facts that you should know is that when you have parallel lines, opposite interior angles are equal. So these guys right here, or maybe I shouldn't say opposite, it's alternating. Is that what it's alternating. Opposite interior? Alternating interior. I forget what it's called right this second. These interior angles are the same, whether you call them alternate or opposite. Alternate interiors. I think it's alternate because the interior angles are the four angles that are interior to the two lines, and those are on opposite sides of this line, which we would call the transverse. So opposite interiors. Those opposite interiors are equal. And so that angle of depression that we're looking for, that's the angle we're trying to solve for. That's the same as this angle inside the right triangle that's given. That's called the angle of elevation. And so if we solve for that angle, right, we can call that angle theta because it's equal to, in measure, that angle up there. So we call that theta.
I looked it up. It's alternate interior angle.
It's alternate? Thank you. Alternate. Yes. Alternate. Not opposite. Okay. Alternate. Thank you. Yeah. Alternating interiors. And what trig function should we use? We've got a hypotenuse and one side, one leg. Sine? Yeah, sine's the right one. So sine of that angle theta will equal 475. That's the opposite leg or opposite side over the hypotenuse, which is 850. So theta, so here's where we were talking a little bit about inverse functions before. So trigonometric functions have ratios as their values, and we would have to use an inverse trigonometric function to find an angle from a ratio. So trig function of an angle gives a ratio. Inverse trig function of a ratio gives an angle. Follow that? So trig function of an angle gives a ratio. Inverse trig function of a ratio gives an angle. So with inverse functions, you move it to the other side. So it's always the inverse of the other side equals your angle. And again, this procedure only works right now only if theta is acute angle. Only if it's acute. So it's between 0 and 90. So now, as long as we're in degree mode, we type that in. And let's see, it says, does it say what to round it to? And it just says, what is the angle of depression? So these are big numbers here. Let's just round to the nearest degree. So what do we get? 34 degrees. There we go. 34 degrees. Not too bad. You just solved a word problem. Yay. All right, so let's take a 10-minute break, and then we'll solve some more word problems. Since you did so well, okay, this is, we looked at this one last class, and I want to do, it always takes at least twice of doing this problem before it really sinks in. So we're going to do it again, but with different numbers, of course. Doing it with the same numbers is not really that helpful. So again, this one is, I refer to it as the nasty algebra problem. It's one of the few problems that we look at solving a system like you did in 121, but it's got a lot of nasty numbers in it. And so the idea, again, is that we're going to build two equations with two unknowns, and then we have to do an elimination or a simultaneous solve thing, a substitution. So whatever technique works best for you, you can use either one. And we're going to change the numbers this time so that you have two different problems that you've solved. So let's take a look at the outer triangle first. The outer triangle is this one. And for today, we are going to convert that angle and make that angle 39 degrees. Not use the 30. And we're going to change this angle over here also. And we're going to call that, let's make that 62 degrees. All right, and we'll change this, make that 900 feet. Okay, so again, the scenario is that we're sailing. We measure the angle to the top of the bridge to be 39 degrees. We sail 900 feet, measure the angle to the top of the bridge to be 62 degrees. And we want to know how tall the bridge is. We want to know what that vertical distance x is. And with the outer triangle, we can use the tangent function. And tangent of 39 will be equal to x divided by the whole base of this triangle. And when we look at the base of this triangle, it has a 900, and then there's a piece that's unknown. So we have to call that unknown something. And I called it y last time. Y seems to be reasonable. And so that whole yellow base is then 900 plus y. So that's our first equation. And then we're going to focus on the inner triangle. And that inner triangle will give us a second equation. So the inner triangle is going to be that one. And the, I guess scroll a little bit. And that second equation will be tangent of 62 equals x over y. So those are our two equations, two unknowns. We can use elimination or substitution. Our goal is to solve for x. Last time we solved for x directly. Maybe this time I'll solve for y first and then plug it back in and get x. It doesn't matter. You've solved enough systems that you know you can solve for the x first, solve for the y first. You back substitute to get the other. So from this equation right here, it's very easy to solve for x. X will be equal to y times tangent of 62 degrees. Whoops. Let's go down. And now let's plug that into the top equation. So we're going to plug that in right there. And that's going to give us this equation. And you could clear this fraction first, which typically is a good strategy. This time I won't clear it until the next step. So there we have an equation, a linear equation with one variable. And that's linear because the power on the y is 1. So it's linear. And we all know that to solve a linear equation, we move all the terms that have the variable to one side, all the constants to the other. We factor if we have to, and then we divide. Okay, so let's clear that fraction. So when we clear the fraction, on the left we'll have 900 tangent 39 plus y times tangent of 39 degrees. Usually with a trig function, you write the coefficient out to the left, so it's not to be confused with what's in the angle. So most folks are going to put the y there instead of here, because then it's like, oh, is that y part of the angle? So usually we'll put the y out in front or the x out in front, the variable out in front. So that's a linear equation. The power on the y's, both are 1 and 1. So we've got to collect the like terms on the left, put the constants on the right. So on the left, we're going to have y tan 39 minus y tan 62. And on the left, I'm going to subtract off this constant. Everyone agree that's just a constant? There's no variable in there. That's just a number. It's an irrational number. Y is showing up in both places. What do? Factor, because we want to have just one y so we can isolate it. Right now we have two y's. So the way you go from two y's to one y is by factoring, the reverse of distribution. So we're going to have y times the quantity, tan 39 minus tan 62, equals 900 tan of 39 degrees. And then our y will equal, our last step is division. So we have 900 tan 39. And all of that will be divided by that parenthetical quantity that's being multiplied by y. So we're going to divide by that whole thing. All of that will be multiplied, will be divided. Oh, I can't erase those parentheses. Yeah?
910, 39, this should be negative or no?
It should be negative when I move it to the right. Did I not make it negative? Ooh, muy mal. Yes, thank you. So that subtracts over to create a negative. That subtracts over, so that should absolutely be negative. Thank you. So that should be negative right there. Good eye. Very good, very good. And then the hard part, type it into your calculator and get the right answer. So remember, and maybe it's good that I have the parentheses left up there in the denominator. You don't need them in this when you stack your fraction, but when you type it in your calculator, you definitely have to wrap that denominator in parentheses so that it's all grouped together. So let's see if we can get the right answer. Minus 900 tan 39, close off those parentheses. Divided by, open parenthesis, tan 39, wrap the 39, minus tan 62, wrap the 62, wrap the denominator, and 681 if we round to the nearest unit. Yeah, if I left off that minus, I'd have a big surprise when I type that all in.
You get a negative.
I'd have a negative number. I'd be like, oh, and then, that's where, last time we talked a little bit, when you get your answer for a word problem, always go back and make sure it's logical. So if we got a negative height, we know something's wrong. Something's wrong. All right. A little bit of algebra. Any questions on any of the steps? Everyone crystal clear on how to get there? How that tan 39 distributes to that denominator that you've multiplied over to the left? The distribution? Everyone clear on that? Tan 39 has to be distributed to each of those terms when you move that binomial over to the left. All right. Oh, more words. Okay, so in this book, they use two different types of bearing. Bearing meaning direction. And the first type is this, where they notate it right down here, south 37 degrees, 37.6 degrees east. So with this first type of direction, you will choose to go either north or south, and then you'll go east or west from that decision. So you can go north and then go east of north, or you can go north and then west of north. You can go south, east of south, or west of south. So that's I believe that's usually used in aircraft navigation. I don't know which is which now. They use this type of navigation in either aircraft or in boats. I thought this was actually traditionally used in boats, but I don't know. Here we're talking about a plane. Oh, no, actually we're not talking about a plane. Here we're talking about, there is a lightning detector. Yeah, so that's not a plane. Usually this you see in boat navigation, this type of direction. But wherever they use it in the real world, it's in this problem, so that's how we have to use it in this problem. So how far is the lightning strike from R? So the idea is that we have these lightning detectors, and they give us a bunch of information about the location of them. So it says that we have a lightning detector at point Q. So we'll put a Q right there. And Q is situated 15 miles west of the fire station, which we're going to call at R. So 15 miles to the west, so directly to the left. 15 miles. So that is going to probably be one side, probably a leg of a triangle, of a right triangle. The bearing, so that's direction, from Q to where the lightning hits due south of R. So they're saying that the lightning is going to hit due south of R, and the direction or bearing to the lightning strike is that, from Q. So from Q, we're going south and then 37.6 degrees to the east. So when we look at our picture here, so we're going to go south and then 37.6 degrees, maybe it's there. That looks like about right. And so then I've got to go far enough that I'm due south of R. Everyone follow that? So due south of R, right there. And the angle that they're talking about is right there. So they said south 37.6 east. So that's this angle. So that angle is 37.6. And here's where our fire is, down here. Oh, not bad. That angle in our right triangle is also 37.6. I should put degrees on there. And so there we have a right triangle with 3 pieces of information. We've got one side and 2 angles. So now we can solve for any piece of that triangle that we need to solve for. Bless you. So any questions on the setup here? And our goal is to figure out how far is the lightning strike from R. So we're looking for this dimension here. Let's just call it D for distance. You're good? Got it?
If you went to the right from Q to R is west, then why did you go right for east as well?
Well, it says that Q is west of R. So I'm saying west is left of R. Yeah, west. Left. West is left. I know that it spells we. That's how I still remember it. Does that answer your question? Does that make sense?
Yeah.
So it says Q is west of R. And that sometimes, with these word problems, it may take 3 or 4 times reading it to sort of decipher. Is it to the left? Is it to the right? Is it below? Is it above? Is the 37.6 here? Or is it here? And you just have to slowly read it. You know, it's kind of like doing a Sudoku puzzle. You figure out, okay, I'm in this block. And okay, you know, just a couple of reads at least. Make sure that you get the picture right. And once we get the picture right, then, you know, then typically you've done the hard part. Typically, drawing the picture is the hard part. Okay, that's 15. Get there. So our goal then is to solve for D. We have to identify the trig function then that will use the 37.6. That side and that side. Those 2 sides are both legs. There's only one of our primary 3 trig functions that uses both legs. That is tangent. So tangent of 37.6 degrees will be opposite. So when we're standing down here at this angle, from this angle's perspective, that side is opposite and this side is adjacent. So that's 15 over D. And then if we multiply and divide, we're in pre-calculus, so we do that in 1 step. In college algebra, they would do that in 2. But we're in pre-calc. We don't do what those pixies do. All right, 15 divided by tangent of 37.6. We type that in right, and I'm getting 24.4. And then let's check to see what we should round it to. That side was given to the nearest mile. So if they don't tell us what to round it to, then we should probably round the other side to the nearest mile. My guess in my math lab, though, is that they probably will say round to the nearest 10. That's my guess for this particular problem. So now that you've got your answer, though, you just have to look at the instruction in my math lab. There's always a little parenthetical thing, round to the nearest 10. All right, I'll put my glasses on and see what I actually typed into my calculator. Oh, I typed in 31.6 degrees. Yeah. So what did you get?
19.47.
19.47, so we'll make that 19.5. Yeah, thank you. So there we go. Yeah, typing in the dark, I couldn't even see those. I thought I knew where, how did I feel like I should know where 7, oh, these are upside down. I was, like on my remote at home for the TV. These are, it's different. I've got the reverse. Question?
How come the 37.6 degree angle isn't that cube?
Okay, so good question. So the 37.6 degree angle with this type of navigation, they're saying the line of sight from Q to the fire, we go south and then 37.6 degrees east. So that angle is outside of our triangle, but what we're doing is saying, let me move it up here a little bit maybe. I don't want it to, oh gosh, that eraser is way too big. 37.6 degrees D. So that 37.6 is this angle right here, which is the same as that angle. So they give us an angle that's outside the triangle, but we use that alternating interior concept. We have the railroad tracks there. We have a transverse here. So those are opposite alternating interiors. So that angle is in the triangle down there. Yeah. And that's one of those things that you've got to read it a few times to make sure you're putting the angle in the right place. Yeah. Any other questions on it? All right, next one. So now 6.3, we're able to, in 6.3, broaden our horizon, and we're going to find the trig function values for any angle. Theta can be any real number. It can be 1,000,000, it can be 50, it can be -50, -100. Up until this moment, we've only been dealing with acute angles, angles between 0 and 90. Now we're going to extend that definition so that this new definition has to hold and match for the old definition for sure. The old definition was the ratio definition, opposite over adjacent, opposite over hypotenuse. And that has to hold, but what this does is expand the range of angles that we can use. So here are our new definitions. We're going to use a coordinate plane instead of just triangles floating off in space. We're going to put our triangles into a coordinate plane now. So we have an xy plane, a Cartesian plane. And what we're going to do is always draw our angles in the following way. We're going to use the positive x-axis to be what's called the initial ray. And for us now, we're going to think of angles as rotated, as a rotation. It's a rotated ray. So we're going to take this as our initial ray. We're going to rotate counterclockwise to create a positive angle, clockwise to create a negative angle. So we're rotating counterclockwise to get a positive angle. And this over here is going to be called the terminal ray. So if we were dealing with what we were dealing with until this moment, all of our terminal rays would be here in quadrant 1 forming acute angles. Okay, but now we're going to go past quadrant 1 and we're going to let that terminal ray be in whatever quadrant it wants to be in. Or even on an axis. It doesn't even have to be in a quadrant. It could be on an axis forming a 90-degree angle or a 180-degree angle or a 270-degree angle. So we're going to measure from the positive x counterclockwise. And then we have to find a point on that terminal ray. We'll just label the point x, y. So that's a point that lives on the terminal ray. Knowing that point allows us to calculate this radial distance. And we're always going to call it r. That radial distance is the distance from the origin to your known point. So that distance r tells us the distance from the origin out along the terminal ray to point x, y. 3 pieces of data there, x, y, and r. And those 3 pieces of data, just like the 3 sides of a triangle, allow us to form ratios. And those ratios will match if we had a terminal ray in quadrant 1, so we had an acute angle. These ratios would all match with opposite over adjacent, all those things. Those original ratios. So we are defining sine to be the y-coordinate divided by the radial distance. So when we're looking at this picture, the y-coordinate in this picture is a positive number. And that positive number divided by that radius, that's going to be sine. Cosine will be defined to be the x-coordinate divided by r. And the x-coordinate is horizontal, and in this particular case, that x is negative. So we now are going to see ratios that are negative. If we're in quadrant 2, we will have negative ratio, always have a negative ratio for the cosine. If we're down in quadrant 3, we're going to have a negative ratio for both sine and cosine because both x and y are negative. R is always positive. R is a distance. So if x is negative, the ratio is negative. If y is negative, the ratio is negative. For sine or cosine. Okay. All right, so let's try this. So we'll take, we've got a point in quadrant 3. So I'm going to draw a ray in quadrant 3. I'll put the point on that ray. That point is -2, -5. It's on the terminal ray. We need 3 pieces of data, though. We only have 2. We have x is -2. We have y is -5. What's the piece that we're missing? R. But we can compute that. It's just the Pythagorean theorem computation. There is a right triangle in here. And if we treat it like a right triangle, and by that I mean, we think of this is a right triangle where this side is 2 and this side is 5. The negatives don't matter because distance is always positive, and that radial distance will be positive. And the formula that we will always use to find r is the Pythagorean theorem. R squared will always equal x squared plus y squared. And if you do include the negative in this next step, make sure that you have that negative wrapped in parentheses. It's really important, and I'm sure I'm preaching to the choir. -2 squared and -2 quantity squared are totally different. -2 squared is -4. -2 quantity squared is +4. Right? So in order for that negative to be affected by that exponent, it must be in parentheses. So that is +4, but that is -4. So if you're going to write down this step, make sure you do it correctly and you wrap the negative up so that it's affected by the exponent. So our radius squared will be 4 plus 25, which is 29. So our positive number, so we don't have to take the negative square root, it's positive, root 29. So we can now find the trigonometric function values, all of them, for this angle. They called it angle theta. So we now use our new definition. Sine of angle theta is going to be the y-coordinate divided by the radial distance. -5 over square root of 29. My math lab will definitely want you to rationalize that, so you would write it as -5 square root 29 over 29. When we take our written exams in the class, and I'm grading them, I don't care whether you rationalize or not rationalize. The only numbers I really care about you rationalizing the denominators for are these types, these special ratio numbers that show up. And we'll see, so these special ratio numbers, 1/2 root 2 over 2 and root 3 over 2, writing them with rationalized denominators is very useful because you can see how they relate to each other. You can see the order of them. Is it obvious that root 2 over 2 is bigger than 1/2 and root 3 over 2 is bigger than root 2 over 2? So you can see that if they all have the same denominator, root 3 is bigger than root 2, so root 3 over 2 is bigger than root 2 over 2. Root 2 is bigger than 1, so root 2 over 2 is bigger than 1/2. And that's going to be really important in a couple of weeks when we start doing the unit circle. The most common mistake here is to do something like that. Is to say, ooh, sine is y, cosine is x. And that's wrong. And it should be obvious that it's wrong soon. We know that sine and cosine are restricted. When we were dealing with acute angles, they had to be between 0 and 1. Now that we're allowing any angle, the restriction grows a little bit, but not a lot. They have to be numbers between -1 and +1. So they still have to be small in magnitude. They have to be between -1 and 1. That's not between -1 and 1. That's not okay. It needs to be scaled by that radius number there, by that radial value. So this is going to be -2 divided by square root of 29. And again, in my math lab, it will definitely want you to rationalize. Tangent is y over x. So that's 5/2. Do you know what 5/2 also corresponds to for that ray? Slope. When you draw your angles in the coordinate plane with a rotation from the positive x-axis, tangent will always equal the slope of the terminal ray. So in quadrant 3, you should have a positive slope. So you have positive tangent values down in quadrant 3. And now our reciprocal functions. To reciprocate for cosecant, it makes more sense to reciprocate that one because the square root's in the denominator, and when we flip it over, it'll be in the top. And we don't have to do any more rationalization. Same here, so this will be negative root 29 over 2, and this one will be 2/5. So that's how we can find the trig function values of any angle. One helpful association is that notice that the y is associated with the sine function, the x is associated with the cosine function, and if you think alphabetically, c comes before s, just like x comes before y. So you can remember that x is going to be with cosine, y is going to be with sine if you think about it alphabetically. All right, you guys try this one. Uh-oh, what did I just hit? Did I break something? All right, so you guys work on this one. And Jess and I will help you if you have any questions, if you get stuck. So draw a picture. Drawing pictures helps a lot. something. So you always have to have an angle so that the sine of theta is equal to your ratio. So that's your triangle. So then the first step is always to find that radial distance from the hypotenuse. You use your to figure out what that radius is for that hypotenuse. So when they tell us that terminal rate, we can either be talking about this positive angle, we can even find the angle, right? You know, so the angle is kind of doesn't even matter if this or that could be theta. It's also true that this angle right here, if we do that angle, which is a negative angle, we're changing the clockwise, the trig function values will be the same. So the idea here is that any angle, no matter how many times you spin around, if you end up at that same terminal ray, we're going to have the same trig function values. So one question that we could ask, we could say, what is the smallest positive angle that has these trig function values? If we wanted to find theta, we could say, what is the smallest theta? So the smallest positive theta would be this one. The smallest negative angle would be that one. But you could spin around multiple times and end up at that. As long as you end up at that terminal ray, all that you want to do. So theta can either be that theta is always going to be a rotation. So theta is coming from positive x all the way to there. This is the smaller one I was talking about. This could also have the negative angle. So any angle is also rotating. So many rotations if you want. Any angle that rotates from positive x this way or this way that ends here is going to be it's going to be your theta and it's going to have the same trig values. So we're going to call those coterminal angles. All right, so let's do this one and clear up a couple of things. Pretty straightforward to draw your terminal ray. There, and to put your point on it, your terminal. A lot of times I'll call that the terminal point. It's on the terminal ray. Finding r is not too bad. You square both, so you get that r is square root of 13. So the trig function values then, if we use our new definitions, we have that sine of theta is equal to the y coordinate over the radius. So that's going to be -2 over square root of 13. Cosine will be the x coordinate over the radius, so that's 3 over root 13. Tangent is the slope. It's y divided by x, -2/3. Or it's sine divided by cosine. If you do sine divided by cosine, you would multiply the reciprocal of that fraction by the sine fraction. The 13s in square root would cancel, and you get -2/3. Do it that way. And then we do our reciprocals. This will be -√13 over 2. This will be √13 over 3. This will be -3/2. You can rationalize those if they weren't. These ones I didn't rationalize. So these ones for my math lab, you should rationalize them on our first test. I don't care if you rationalize them or not. Either way, it's fine. It doesn't matter to me. But my math lab will definitely want them rationalized. So now the question is theta. We haven't identified theta. We haven't found theta. We just found the trig function values of theta. And it just said that theta is on this terminal ray. So we didn't even sort of decide whether it's a positive theta, a negative theta, and it doesn't matter. If we now are thinking of theta as a rotated ray, the ray that we always start at, the so-called initial ray, is right here. And then we either rotate clockwise, whoops, counterclockwise. That's counterclockwise. We either rotate counterclockwise for a positive angle, or we rotate this direction clockwise for a negative angle. Counterclockwise positive, clockwise negative. But it doesn't matter. Either one of those angles has the same terminal ray, has the same terminal point, has the same 6 trig function values. And we can figure out what that angle is. Like we could ask ourselves, what is this smallest positive angle? Or what is this smallest in magnitude negative angle? And we would do that by typing in inverse sine, inverse cosine of these numbers. We have to be a little careful now, though, because we're not dealing with an acute angle. So I don't want to do it right now. We'll learn a technique that will work for these angles that are not acute. But it's not quite as simple as just typing it in. We have to do a little math. I'll show you. We'll figure it out soon. But at this point, those two angles I've drawn, or this angle that rotates around multiple times, as long as it has the same terminal ray, same trig function values, no matter what. So you could rotate a whole bunch of times. All right. So for the following angles, state the quadrant that the terminal ray lies in. And these aren't meant to be super hard, but we want to make sure that it's clear on the direction of rotation. So negative 14.3 degrees, that means we start at the positive x-axis, and because it's negative, we're going to rotate clockwise. But we're only going to rotate 14.3 degrees in the clockwise direction. So what quadrant is this terminal ray in then? Yeah. So negative 14.3 degrees, this one is in quadrant number 4. Negative 120 degrees. So again, we start out over here, and then we rotate clockwise because it's negative. I just went 90 degrees negative. So right, there's negative 90, and then I've got to go 30 more in the same direction. So roughly there. So that is a rotation clockwise. That is negative 120 degrees. And that is in quadrant 3. Next one, 1075. That one incorporates multiple rotations. So we've got to be a little bit more careful. So one rotation is 360 degrees. 2 rotations is 720 degrees. 3 rotations is 1080. So if you watch winter sports, those numbers are probably familiar to you. 1 rotation, 2 rotations, 3 rotations. 1.5 rotations would be right in there at 540. So when we look at this number, we're rotating counterclockwise because it's positive. So when we go around, there's 360. There's 720. Now 1080 would take us all the way around again, but we're going to stop just shy of 1080. So our terminal ray would be right there. And what quadrant's that in? 4. Yeah. Okay, so let's do an extension of that idea. So here it says find 2 positive and 2 negative angles that are coterminal. Coterminal means they share a terminal ray. They have the same terminal ray. With the given angle. Answers may vary, of course. Obvious answers may vary because there's an infinite number of positive coterminals and an infinite number of negative coterminals. Most of us are going to go to the subsequent ones instead of adding, 1080 every time. That sounds like a pain. So if we do it systematically, the next positive coterminal angle would be 74 plus 360. That would be the next consecutive positive angle for rotating counterclockwise. And then similarly, the next one after that, we would add 360 again. And we would get 794. So those two angles are positive coterminal angles. If we wanted negative coterminal angles, we're going to subtract. So let's start with 74 again. We're going to subtract 360 degrees. So somebody do that for me. Negative 286?
Yeah.
Thank you. And then if we subtract 360 from that, what do we get? Negative 646. All right, so those are two negative angles that are coterminal. All those angles have the exact same trig function values. Coterminal angles, same trig function values, always. Doing one of those I think is enough. You get the idea. So for negative 81, subtract 360, subtract 360 for two negative coterminals, add 360 to get two positive coterminals. All right, this takes a little more thinking. So terminal side of angle theta in standard position lies on the given line in the given quadrant. Find trig function values. So let's draw a picture. So a little review of algebra again. So that line, 2x plus 3y, it goes through the origin. 0, 0 satisfies that equation, so it definitely passes through the origin. And for a line, of course, you need 2 points. Bless you. So if we're looking at 29 here, we got 0, 0. We need to pick another point. There's several ways you could, bless you, several ways you could do this. You could write this line in slope-intercept form. Totally reasonable. You could do that. You could just pick a number for x and solve for y to get a second point. Lots of things you could do. If you picked a number, this might be the easiest place to look to pick a number that's so you don't deal with fractions. You could look here and say, oh, if I pick a 3, those will cancel and I'll get a negative 2. So 3, negative 2 will give us that. So the line that we're looking at then is this line right there. But they tell us, and we need to know which quadrant to focus on. Because a terminal ray is a ray. It's only in one quadrant. So it says quadrant 4 for that one, so we're down there. The x and y coordinates here are 3 minus 2. So the r value looks familiar. So 9 plus 4 is 13, so this distance is square root of 13. That radial distance from there to there. Square root of 13. And now that we've drawn the picture, and we've found our radial distance, the hypotenuse, if you drew a triangle, if you do draw a triangle, I want you to draw it this way. Draw it so that it's like that. Don't draw it down here. What we're going to see soon is that we always want to include the horizontal axis as one of the legs. So that triangle, sure, it's congruent, but if you're going to draw a triangle in any of these pictures, get into the habit of always using the x-axis as one of the legs. We'll see why in a little bit. Okay, so now we can do our trig function values pretty easily. The trig function values for this angle, whoops, yeah. That goes there. How do I get that one back? And we're calling this just theta. And they just asked for the first 3. So what's sine of theta? negative 2 over root 13. And so again, remember, if it's helpful to you, alphabetically, cosine and sine, you think about C before S, C goes with the x coordinate, S goes with the y coordinate. So then we're going to have 3 over root 13, and then tangent y over x, so negative 2/3. Didn't ask for these, but we can find them pretty easily by flipping these over. Get those ones. Just check. I can't remember how many slides we. Yeah, we'll go to the next one. All right, any questions on that? Graph our line, find a terminal point. And do you see why it doesn't matter what terminal point you pick? If you pick another terminal point, so let's suppose you pick this terminal point that created this triangle out here. Do you see why it doesn't matter what terminal point you pick? What's true about this blue triangle and this red triangle that's in here? Yeah, they're similar. They're similar triangles, and similar triangles have the same ratios. So that's why it's not going to matter which terminal point you pick. All right, so you guys try this one. A function value and a quadrant are given. Find the other 5 function values. I'll give you a hint. So draw a ray in quadrant 3 and put a point on it. And see if you can piece together what they're asking for. Sine of theta is negative 1/3. How can you use that ratio? How can you use that ratio? So I'm going to do that too. So you know you need 3 pieces of data. You need an x, you need a y, you need an r. And I claim that that fraction that they give us, sine of theta equals negative 1/3, is enough. Is enough to generate those 3 pieces of data, which you can then use to find your ratios. Anyone choose an R value yet? 3? So you said positive 3?
Yeah.
Okay, so I've heard a positive 3 chosen for R. And what does that make your y coordinate? Okay, so does that match with what some of you are thinking? We know that sine is y over R, so we know that's negative 1/3. That's given. Does that match for everybody? What about, is there another, did anyone else choose a different y value? Another one that you could have picked, you could have said, hey, I'm going to let y be negative 1/3, and then the radius would be 1, right? Because then negative 1/3 divided by 1 would also give us negative 1/3. So those would be the 2 kind of standard choices. Now, if you've picked this as your y value, then you have to find your x value, so we'll use the Pythagorean theorem to find the x value. And the x value is going to be, now here we have to do plus or minus root 8. So we get plus or minus 2 root 2 if we simplify that square root. And which one should we choose? Negative, because we are in quadrant 3 where x's are negative. So here's an example where we have to do the plus or minus, and then we select the negative because we're in quadrant 3 where x is negative. Negative 2 root 2. And now we're golden. Now we have 3 pieces of information. That's plenty. So cosine is then negative 2 root 2 over the hypotenuse that we generated, which was 3. Tangent is negative 1 over that, so 1 over 2 root 2. And of course, you can rationalize it, and then you can flip these over. And of course, you can rationalize them if you need to or want to. All right. Let's see. So and then there's another one like that. Let me see what I have on the last. I can't remember what I had on the last slide. Reference angles. We have. Yeah, we'll do those. We'll do those at the beginning of class on Tuesday of next week. So let's do one more of these now. Let's do one more of these, and we'll call it. We'll call it a Thursday. Okay. Oh, whoops. They use a different angle. That's a Greek letter phi or phi. Some call it phi, some call it phi. And I put a theta there. Obviously, those angles should match. So we're going to do it where we're going to pretend that's a theta. All right, so same idea. See if you can get this one. So you've got cosine of theta is given to be 3/5. And we are told that our terminal ray is in quadrant 4. Quadrant 5. It's time to call it a Thursday. When the coordinate plane turns into 5 quadrants, it's new math. Quadrant 5. It's below the others. Quadrant 5. Somebody pick an R. 5's the natural choice. And then where would the 3 go? X, exactly. So that would be probably the most natural choice. And then you don't know why. So we Pythagorean theorem it. Square the 3, square the y, square the radius. Y squared is 16. Y is plus or minus 4. Here we have to choose. And what do we choose? Yeah, we're in quadrant 4 where all the y's are negative. So we choose choose negative 4. And then we're good to go. So by definition, sine is the y value, negative 4, over the radius value, 5, negative 4/5. Tangent, what would tangent be? Negative 4 over 3, and that also corresponds to the slope of the terminal ray. So it's the y value over the x value on the terminal ray, and because this ray goes through the origin, that's also the slope of the line. And then we can reciprocate. Don't have to deal with any rationalization there. All right. It's a Thursday. Have a good weekend. Get cranking on your homework.
Tutoring Tuesday morning.
Tutoring Tuesday morning with Ms. Fancy Pants, 1406, right over there, 9 a.m. Study group. That's how you learn math. Team sport. How's it going? Very good.
So just want to make sure it was
Oh, yeah.